Thank you, Mr. Chairman. My name is Kazuki Ohashi. I'm a master of Nagoya University. Today I will be talking about joint estimation of high-resolution image and depth maps from light field cameras. First, I'm going to talk about overview our research. Left is a raw image captured by a light field camera. Top of left in this image is close up. As you can see here, the raw image is special. Matched with sub-aperture images. Sub-aperture images are produced from the raw images. These are low resolution. Thus, in our research, high-resolution images are produced from the multiple sub-aperture images. Then let me mention what light field cameras are. Light field cameras are attracting much attention as tools for acquiring 3D information of a scene through a scene camera. In light field camera, a microarray is inserted between the sensor and the main lens. This structure enables some applications. Some light field cameras are commercially available, such as Lightro. The application of Lightro are digital refocusing and free viewpoint image synthesis. Let me show these applications. In the digital refocusing, we focus on the point which we click, as you can see here. In the free viewpoint image synthesis, we can see the image from the viewpoint which we choose. Light field cameras are able to capture several views of a scene simultaneously. These images of several views are sub-aperture images. I will explain how to convert raw image to sub-aperture images. This is a raw image captured by a light field camera. A micro lens is close up. So there are multiple pixels behind the micro lens. Sub-aperture images are formed by extracting a pixel at the same position from each micro lens and arranging all of them. For example, this sub-aperture image is formed by gathering pixels of position of 1. And then the position of 2 is gathered. Then the position of 3 is gathered. Next. Left image is a raw image of light field camera. And the right image is arranged sub-aperture images. As shown these images, sub-aperture images can be regarded as a set of rectangular images whose viewpoints are arranged on a 2D surface corresponding to the aperture of the light field camera. And thus, sub-aperture images are stereo images. And the resolution of sub-aperture images is the number of micro-lens because pixels of sub-aperture images are arranged by extracting a pixel from each micro-lens. In light field cameras, the number of micro-lens corresponds to the angular resolution, and the number of pixels behind the micro-lens corresponds to the position resolution. Thus, the angular resolution and the position resolution trade off under the fixed resolution of the image sensor. So the resolution of sub-aperture images is low. For example, in our case, the resolution is 325 by 377. This is main drawback of light field cameras. Super resolution is a technique that enhances the resolution of images. Flow of super resolution reconstruction is as follows. First, we register multiple observed images. Secondly, we estimate and optimize high resolution image by using the registered image. Super resolution reconstruction is very sensitive to registration error, so accurate registration is necessary. I will explain the purpose of our method. To overcome the low resolution of sub-aperture images, we enhance the resolution of sub-aperture images by using super resolution reconstruction. In super resolution reconstruction, accurate registration is necessary. The registration is equivalent to depth estimation. And thus, we propose the method that jointly estimated high-resolution images and depth maps. In our method, we increase the resolution. In our method, we increase the resolution of the image and depth maps simultaneously. Here is what we did in the proposed method. First, we calculate the initial depth map and the initial HR high-resolution image. The initial depth map is calculated by stereo matching among sub-aperture images. So the initial depth resolution is limited by the resolution of the sub-aperture images. And the initial high-resolution image is calculated by bicubic interpolation of a sub-aperture image. After that, we perform a depth refinement. In the depth refinement, the depth map is optimized, and then we increase the depth resolution. And then we perform super resolution reconstruction. In the super resolution reconstruction, the image is optimized, and then we increase the resolution of the image. As shown this, we perform the depth refinement and super resolution reconstruction alternatively. In our method, this energy function should be minimized. This energy function represents the square error of sub-aperture images and the deteriorated image from estimated high-resolution image. Procedure of minimization of energy function is as follows. First, give the initial values to high-resolution image and depth map. Then we perform depth refinement. In the depth refinement, provided that X is a fixed value, optimize D. Then we perform super resolution reconstruction. In the super resolution reconstruction, provided that D is a fixed value, optimize X. And finally, iterate step 2 and step 3 until convergence or for a fixed number of times. In our method, the super resolution reconstruction is implemented by image processing operations. We use the gradient descent method as described first and second equation. The matrix is decomposed into as described third equation. Each matrix represents subsampling, motion, blurring. Likewise, transpose of AK is decomposed into as described force equation. It is trivial that the operation of AKX can be implemented by image processing operations. The image of AKX can be blurred, shifted, subsampled. However, multiplication trans of AK does not seem to be straightforward. If transpose of AK can be implemented by image processing operations, the super resolution reconstruction can be implemented by image processing operations. Thus, we add some assumptions to each matrix decomposed from AK. The blur matrix B is assumed to be spatially invariant and symmetric. The motion matrix MK is assumed to be pixel shift limited integer values. Regarding transpose of B, transpose of B is equal to B, so transpose of B is implemented by smoothing filter. Next, transpose of MK represents pixel shifts that are opposite to MK. Transpose of D represents upsampling matrix inserting 0 elements at regular intervals. All of these can be implemented by image processing operations. So, transpose of AK and the super resolution reconstruction can be implemented by image processing. We perform depth refinement to minimize the energy function. In the case that we optimize this D2, we change the all depths in the block. And then we compare the pixels of high-resolution images to the corresponding pixels of sub-aperture images. Which correspondences are given by depth value, and adapt the values which reduce the difference between the compared pixels. We have conducted an experiment to confirm the effectiveness of our method. We use a light field camera. The resolution of raw image is 3280 by 3280. And the resolution of sub-aperture image is 325 by 377. The used number of sub-aperture images is 25, and the resolution of super resolved image, the image is 975 by 1131. And first, we compare the estimated high-resolution images. Left image is calculated by bicubic interpolation. Center image is super resolution reconstruction without depth refinement. Right image is calculated by the proposed method, which is super resolution reconstruction with depth refinement. Let me show close-up of the last images. Left is bicubic interpolation, center is SR without depth refinement. Right is the proposed method. Compared to these, we found the proposed method can produce clearer images. Left is the depth before depth refinement, which is calculated by stereo matching. Right is the depth after depth refinement. And this energy function E is plotted against the number of iterations in this view graph. Blue line is using super resolution without depth refinement, and the left line is using the proposed method. In this graph, the proposed method reduces the energy function E compared to super resolution reconstruction without depth refinement. And now let me summarize my presentations. We proposed a method of joint estimation of high-resolution images and depth maps from light field cameras to overcome the drawback of light field cameras. And the key concept is that the depth resolution should also be increased while the super resolution reconstruction, so that depth refinement is conducted alternatively with the resolution enhancement of the image. As the experimental result, we improve the high-resolution image compared to the super resolution without depth refinement. As a future work, we will improve the depth refinement to obtain more accurate depth map. Thank you for your attention.
Thank you so much.